And we calculated the current last week, right? 0.64 millidarcies. We got that far using this equation right here. And I promised that I would do the second part of the problem tonight, which was skin. And I wanted to just talk a little bit about skin first. I'm gonna keep checking over here and see if I can't hit record, but it doesn't look like I can. So I'm going to repeat myself probably several times, but we used to delve in the world of radial flow. And nowadays, most of the wells you'll run across, depending upon where you're going to work, are going to be multi-frac horizontals, and we're going to deal with linear flow. All that will be on the final exam. In this chapter, and also in the next chapter, we have pressure buildup examples for radial flow and for linear flow. And historically, before refraction wells, all wells were radial flow. We drilled a well and we had radial flow as depicted in this pie slice diagram. Can everybody visualize that that's a reservoir? And the cutaway there is where a well bore would be, and then the flow into that well bore would be radial. When we drilled wells that were radial wells and produced them, we have a fluid in our well bore. And who can tell me what that fluid is?
Drilling mud?
Drilling mud, yes. And what is one of the purposes of drilling mud?
Preventing kick,
Preventing a kick. And how do you do that?
keeping mud weight density, have your hydrostatic head greater than the.
This is going excellent, right. We drill over balanced. The weight of our mud is greater than the formation pressure. If we run across a porous formation, what's going to happen to that mud?
Leak into formation.
It's going to leak into the formation, and that's what's depicted in this picture in the shaded area. Now, if that formation originally had hydrocarbons in it and maybe some initial or irreducible water saturation, will this portion of the formation produce as well, worse, or better than it would before we drilled it and invaded it with drilling mud?
Worse.
Worse. Because part of the pore space is now occupied by drilling mud. That blocks that portion of pore space that would have been available for hydrocarbons to flow. That all makes sense, right? So we call this skin. We always have and always will. And so there's definitions there. There's a radius that drilling mud invaded into, and if our formation had a permeability of K, we had a permeability now. And here, this is a little bit awkward, but what we're really probably talking about here, both those subscripts should be hydrocarbon. So if it's gas, it'd be gas permeability. If it was oil, it'd be oil permeability. But the permeability that we're interested in the fluid that we're trying to flow out of the reservoir. Now, and again, I'm going to keep checking over here to see if I can start recording. Ah, it is recording, look at that. I'm still not getting anything here on the band on my audio, even though it looks like I've got audio in the room, which I didn't last week. Okay. Now, let's just for the heck of it talk about a different scenario. Let's say I've drilled a well, and let's say I drilled underbalanced, which we sometimes do. Why do we drill underbalanced?
So we don't damage the formation.
So we don't damage the formation, okay? And then there's another reason, of course, this is a little bit more expensive operation, but if we have our surface drilling situation where we can better manage kicks, where we have a separator on site and we actually have either the permits to flare or we have temporary storage vessels to store, produce fluids if we do get a kick. And why would we ever want to spend all that money and do that?
Drill faster.
Pardon?
Drill faster.
Avoid.
Sometimes the mud weight may adversely affect, but that's not the primary reason.
Avoid differential sticking.
Avoid what?
Differential sticking of the pipes.
Okay, you guys are drilling engineers. You're killing me.
Avoid damage.
Huh?
Avoid damage.
That's already been said.
Reason why would we drill?
Why would we like to drill under balance? It's nicknamed drilling for kicks.
Drilling for kids, that's, is that?
Yeah, why do we drill for kicks?
To see if there's gas there.
Huh?
See if
Yeah, to
there's-
see if there's gas there. Okay? So, if I don't have to even look at a hot wire or a shell meter or have a geologist on site looking at cutting samples. If I see oil and gas coming out of my separator, I've got a producing formation. It's actually showing its commerciability by flowing it, where if I drill overbalance and just log it, I'm still wondering, maybe is this the right petrophysical model to evaluate this formation with? Maybe it's a carbonate, maybe it's a mudstone, so I don't really know which model to use it for. It's really hard to determine the commerciability of formation just with petrophysics. Once you're in a developed area, then you figure out what petrophysical model works. But if you're drilling exploratory wells, then sometimes you drill for kicks. Okay, but you got more. It's going to cost more. You got to have a lot better surface control for it. Okay, so let's assume we were drilling for kicks.
Excuse me.
Yes.
So what about we get a kick? How do we contain it? How do we manage it?
At the surface with surface back pressure. We don't manage it. We love it. We don't manage it.
You circulate the kick out?
Yeah, we're producing. This is, I'm calling headquarters. We got a well. Okay? Eventually, we may have to kill the well, or, control the pressure. But we try to do it by conventional drilling operations. The only way we can control the downhole pressure is with mud weight. But if we're coming up, because coming up the backside, it's usually open to the atmosphere. It just goes over the shale shaker and into the pit. It's open to the atmosphere. But if you have a closed system and going into a separator, then you can control the back pressure. So I have two controls on the pressure at the bottom. I can choke back the surface conditions on the outflow on the annulus side. So I have another handle. I don't necessarily have to mud up or weight up my mud to control the bottom hole pressure. Okay, so I was just trying to generate a scenario here where we may not have damage. Now let's say it's a limestone formation. And what I do is after I have ran casing in my well, I've determined this is going to be a producing well. I got my drill pipe out of the hole, my case in the hole, my drilling rig is left location. I perforate my well and I inject acid. And because acid and limestone react, and it etches away some of the limestone. And the idea is to give me improved near wellbore permeability. Okay, so if we have damage, we're gonna end up with a positive skin. And if we have near wellbore improvement, like we may have if we acidize limestone or dolomite formation, we may have improved performance, and that would be calculated as a negative skin. So the next thing we're going to do is we're going to calculate skin, and I'm telling you why we're calculating skin. If skin is a very high positive number, then maybe we want to somehow alter our completion. Or what we may want to do if we've acidized is evaluate the effect of the acid. If we pump some acid in there and skin is still near zero, maybe the next well we inject more acid to try to get a better completion. But again, the near wellbore area is a bottleneck for all the producing fluids to come in. So when we're vertical wells only, this was an area of big concern. So permeability of the formation, very important thing. Near wellbore damage or improvement, also important. So here throughout chapter 6, we're almost always going to calculate permeability, and then the next thing we're going to do is calculate skin. And in radial flow, the time transformation, again this will be on the final exam, that we normally use is
Similar.
semi-log plot. So we take the logarithm of time. And
Can you
in
say that last comment again?
the time transformation that we use for radial flow is,
Oh, okay.
yeah, semi-log. Now I lost my train of thought. So when we're plotting these variables, we normally get permeability from the line.
Middle time.
The what?
Middle time.
Middle time region. That's good. You've been doing the reading. From the slope of the line during the middle time region, after wellbore storage and before boundary time effects. I'm glad you added that. It's not the whole line, it's only a portion of the line. So, and then we have some checks and balances. Normally, and I've done a lot of these, we rush to judgment. We go, this is the middle time region, and we calculate a perm in the skin, and then if that's the perm in the skin, then we can do some calculation checks to see if that does tell us when the middle time region did start and when it should end, and then we back check to see if that's where we took the data in. It's hard to do this beforehand. So usually we rush to judgment. I've looked at a lot of these, this is the middle time region. And then when we get a permeability calculated, we can determine if it's that permeable, then yes, our wellbore storage period should have ended by now, and we indeed did pick the right middle time region. Very good point. Okay, so now we're all good at skin. Let's calculate skin. Oh, so we get the perm from the slope, and we normally get the skin from the intercept. So almost always we're doing a straight line analysis. So slope gives us perm, we got the right slope. And the intercept gives us skin. I got two mice up here.
Did you say the intercept?
Y-intercept. Okay, so here, I'll pull it up here.
We take it as 0 or the 1 hour.
Okay. Well, what is the time units for well tests? This is on the final exam. I already told you this. What are the time units for chapter 6?
Time.
Hours. And what is the log of 1?
0.
So, piece of 1 hour is the y-intercept. It's gonna be a little bit different on a pressure buildup, but on a pressure drawdown, it's easy. The first two examples we're gonna do is drawdown. When it gets more complicated, I will definitely emphasize the point that we need P sub 1 hour. Okay, so here's our little graph right here. I'll go ahead and put it in our PowerPoint. And where are we? We're up here. Permeability and skin factor from a multi-rate test. Okay, so, no, that's 6.2. But we are gonna get to 6.1 a little bit later. I'll move it down here. Okay, so here's our equation for skin and perm. On our multi-rate test. Let's move some of this stuff out of the way. I'd like to move. And this is the same equation I calculated before. I'm going to delete it. Oops, it might be deleted. And because I also have the skin in here. So, 6.46. And especially on this particular plot, it's this B-intercept is, it's not apparent that the B, this is the B I'm referring to. Let me go back to PowerPoint because that doesn't get, my mouse doesn't get recorded. So knowing that, I'm going to, there's so many different, Phil. No Phil. How come I don't see no Phil? Oh, that's because I haven't opened the menu. Okay. The B I'm referring to is, if I can get it. Is this B right here? Okay. That's the intercept. That would normally be P sub 1 hour. But we're doing a multi-rate test, and we're using this time transformation . Do you remember that we actually used, that we wrote a VB function called super radio, and we took the log of a time difference in there. So it's not apparent that this is P sub 1 hour, but we took the log of time, and I think we did a comparison, didn't we? Here's the log of time, and here's the time rate function. And for 1 hour, I think we're at 1 hour. No, we're not, we're at 6 hours. At 6 hours, it's the same because there's only one term in our summation term. These become different as we have more terms. But on our plot, right here, our intercept will be, the logarithms have already taken place. It's built into our function. Let's just go look there so that. I got a module 1. I never like module 1s. Don't worry about these things. You'll never use them. I'll give you anything you probably need. Super radial. We take the log, so that we don't have to make a semi-log plot because we've already taken the log in our function. So these are logs. So the intercept is down here. Now, I think I've already gotten the slope. And you see this matches right from my regression line, 2172, 2172, and I use it using the VB function of the known y's in blue, the pressure function, and the known x's, the time rate function. Now I'm going to do the same thing for the intercept. Okay? I've already made it, I've already got it. So I've copy pasted, changed the name from slope to intercept, and I have that intercept. So that intercept in the equation that I'm going to be using here is called B. And a lot of the other problems is going to be piece of 1 hour, okay? But here it's called B. So now I'm pretty much ready to use this equation for skin. Skin is 1.151 B slope. We got B and we got slope. You see, we calculated permeability. It's going to be in our skin equation. We always have to calculate permeability first before we can calculate skin, because permeability is in our skin equation. Is that obvious? Then we got porosity, viscosity, compressibility, total, and RW squared. I bet you everybody can tell me what we approximate total system compressibility as.
Gas saturation.
Gas saturation times gas compressibility. Okay, now these bars, these over bars mean an average reservoir pressure. And as the textbook points out, usually on an initial drawdown, we assume initial pressure is the average reservoir pressure. In other words, it's like taking an eyedropper out of the bathtub. We probably aren't going to change the fluid level of the bathtub. So the average pressure is the initial reservoir pressure. So although it says average there, we're probably going to be using initial gas compressibility and initial gas viscosity. I don't think we've calculated those terms yet. Seems like a lot of my work's gone here, or I never did it. I do this for a couple of reasons, but we got total system compressibility. Was that given in the problem?
Yeah, I think so.
It was.
It was?
Yes.
Okay. And then we calculated a gas compressibility, and we let that use those two numbers to calculate our gas saturation, because total system compressibility divided by gas compressibility gives us gas saturation. If you take that denominator gas compressibility over here, you get SGCG, which equals CT. So on a lot of these problems, I'm going to back calculate the gas saturation from a fluid property calculation of gas compressibility and a CT that's given. That's why we did a lot of this stuff in Chapter 1, is so that we can realize what we're doing here in Chapter 6. If they didn't design the problem very well, because a lot of times they don't give us the gas saturation. If they didn't design the problem very well, we're not going to get a gas saturation that's between 50 and 100%. We might get 130% or something like that. So we may have to make some adjustments. I haven't checked every problem, but I think we can usually get a gas saturation from a fluid property compressibility calculation and a given total system compressibility. Okay, I got CT. Did I ever calculate gas viscosity? Oh, I have. Oh, they gave it to us, right? 0.0286. Okay. And they gave us the wellbore radius. We all know what a wellbore radius is now. Okay, so here is let me get my pen here. Here is the center of the wellbore. and it goes out to this radius, and this radius is usually the inside diameter of the casing. So if we're doing a real world problem, we find out the weight and grade of the casing, and it usually has a nominal diameter, which is approximately the outside diameter. Then the thickness, the weight and the grade will give us the ID. But that's the radius that the reservoir sees the wellbore back pressure at. So if I lower pressure bomb the gauge, you get a PWF, the pressure of the well flowing. It extends out to the wall of that casing, which is the inside diameter of the casing. Okay? And how do we find out the inside diameter of the casing from the nominal diameter and the weight and the grade?
Albert River.
Very good. Halliburton Redwood. So that might be a little too fast for everybody here, but we can find that real quick. You should put this on your desktop. Redbook, that's what I'm looking for. If you're in the field, you might want the mobile app. So, technique, dimensions and strengths, I think is where I want to go. How come my thing isn't on? I got to download it.
Yeah, it used to make you download it. I don't know if they've got it.
Yeah, you got to download it. Okay. I recommend that this is where you're going to get your data. You can find this in books, but one thing about the Halliburton Red Book, because I had the Red Book in my office because it's been around for so long. They have changed and added new casings. And when they add and change it, you're always updated. But I thought I'd be able to show you an example without downloading it, but.
What did you want? I've got the drilling notebook open.
Well, what we could do, if we wanted to, is we could back calculate what casing this well probably had from its RW.
Oh, okay.
But I'll leave that as an assignment to the advanced student. Okay, so we got a wellbore radius. What else are we missing? We got viscosity, compressibility, and then we have a constant. So let's calculate skin using this equation. Skin. See, that's right where we left ourselves. We left ourselves with a little blank here. Equals. And I recommend that if you got time, you put this in a little VB function, because once I do it once and get the constants right, see, I already typed in the wrong number. Once I get these checked, I get the same number. Okay. B is our intercept. I actually even marked it B, divided by M prime. I even marked it M prime. Okay. Minus the log of perm. We've got to calculate perm from the slope before we can do this. Divided by, and then I'm going to open another paren for everything in the denominator, porosity, times gas viscosity that was given, times CT that was given, times RW squared, and wellbore radius. And it should be on here somewhere, isn't it? I didn't enter it. Let's put it right here in B12. So I'm going to get a zero divide when I hit enter, but then I'll go back and put it in there. But I got to square that term. I got to close the denominator on my, or the paren on my denominator, close the paren on my logarithmic function, and then I add, if I can remember right, 3 point what? 23. And then I got to close my paren because that's all multiplied by my coefficient of 1.151. just like I said, I'll get to divide by 0 until I enter the wellbore radius, which is given the problem as what?
0.225.
0.225?
Yes, sir.
Okay, so, and what does the textbook tell me my skin is? .6. Okay, and they gave me 0.61 for perm and 0.26. I got 0.64 and I nailed it on 2.6. Okay, so these problems aren't very hard, Deanna. Hopefully I gave you enough information to where these numbers come from in reality. And we're going to continue to work on these types of problems. And we'll work through radial flow and also the types of tests that are normally run. The next one we're going to look at is a constant constant pressure drawdown. We've just looked at a variable rate drawdown. And in addition to drawdowns of several types, we have buildups of several types. And engineers used to really like buildups because the data was smooth. Because it's hard to keep a well producing at a constant rate and or a constant pressure. But should I zoom that in a little bit? Is that the problem? Pretty much used everything on the spreadsheet to calculate skin. I should have given you a little bit more time there.
Do you have impurities there?
If I don't, I should. Look at that. Oh, and you know what? For some reason, I wanted to show that I was using impurities, and I gave myself an H2S of 10 to see what that was. Remember that vaguely? So I'm going to change all my answers. Now I got to skin it to, I wasn't showing enough decimal points on my permanent skin. But now I'm just going to highlight my results. And incidentally, when you do take a computer test, here's what I recommend you do. If this was the problem you took, I'd take your whole spreadsheet and make sure nothing's highlighted on it, and then come in, and if I ask you, just like this problem is, what permanent skin is, I want to be able to find it that easy. Wouldn't hurt to give me that and that too. That's the way you turn in a spreadsheet if I gave you this problem on a test. Perm is 0.65 and skin is 2.6. And the answer is wrong if you give me more than 2 significant digits. I'm joking, but in the real world, we hardly know anything in petroleum engineering more than 2 significant digits. If anybody tells you they know porosity more than 2 significant digits, I don't know where they're coming from. Kern, typically in order of magnitude. Okay, I was going to go into a little bit why we like pressure buildup data over drawdown data, but I'm going to defer that until we get our first buildup. Yes?
Those VBA equations that you showed us and that you developed, are you going to share those with us?
Most of them aren't even for this class. I think they're in a file called superposition.
And was that on our D2L? Probably not.
No, most of those things are maybe works in progress.
Okay.
But it'll either be like a 5-liner that we'll write in class, or it'll be pretty complicated and I'll give it to you.
Okay.
I'll just wait and see how we go. I can give it to you on the fly.
Could you highlight that real quick? I just want to make sure I have everything selected correctly.
My skin calculation?
Please.
I'm using CT, mu G. I never announced what .225 was. You told me that's what RW was, right?
Yes.
So
Wellbore
Point.
radius.
for the RW, the number is
0.255.
.255.
Yeah, in the book it's .255.
Well, see, it didn't have a big effect. The reason it didn't have a big effect is I take the log of that term, okay? That's like finding out what the order of magnitude is, okay? Basically, this calculation for skin is going to be dominated by B over M prime. Because we take all those factors, even though I changed it from 255 to 225, I'm taking the log of that, okay? So the log of those two numbers, the relative difference was not very much.
Dr. Carr, can you open the textbook, the example solution? And in the textbook, the solution shows that it's minus 3.23.
No, but the skin is 2.6.
Yeah,
You're right.
No, in the original equation though, Boyd, yeah, in the solution, for some reason, I think it's mathematically, but that original equation does show it as plus 3.23. But when you get to the equation,
Equation 6.51.
And it's a little tricky here because they got these tables and they don't have, it is a positive 3.23 here. In that table, it's positive 3.23 here. Yeah, I think the book has an error. Here it's positive 3.23.
If it changes, it's way off.
yeah, I bet you that's gonna
And
be a
somehow, probably due to the wraparound, it got switched to a negative, but it is a positive. Again, that's why I love Visual Basic, is that if I can get it right once, whether it's positive or negative, and can check my work, then I never have to question whether that's a positive or negative number based on something that I see. It would prevent me from making this kind of mistake. There's other errors in this book, but there's errors in almost all the books we use. But go ahead and correct it in your copy. Pretty hard if you've only got a soft copy. That reminds me, I need to get an Acrobat version that I can edit. Okay, any questions on 6.1? Oh, let's see, I'm gonna probably come back and finish something here that I didn't do. And I want to start on my next problem, and I'm going to come back and finish this if I remember. But we're always interested in a radius of investigation. Okay? And that'll be in feet. And I'm going to, there's a couple of equations that we look at there. And let's assume that we're the eyedropper in the bathtub. We've only taken a little bit of fluid out. But the radius that we investigate is going to be proportional to the time of the test and the permeability. The greater the perm, the more I saw. Okay, and the greater the time, the more I'm going to see. So now we've calculated perm, and we know time from the test time. We can see, although we can't see the outer boundary, we can see how much we've looked at in time. And that'd be our radius of investigation. And we can, that would give us an original gas in place minimum. If during our test we do not see an outer boundary and we're continually enacting, we calculated a radius of investigation because we're in radial flow, we can calculate an original gas in place. Now, the equation we'll use will not be the 43560 because that's taking land units of acres, right? Square feet per acre. We're just going to use the radius of investigation, square multiplied by pi, and we'll get square feet. And then we can use the equations straightforward. We're going to come back and do that. But I want to do this next problem first. As usual, I am going to move or copy, well, not in this case. Normally I would, but I'm going to come over here to a blank sheet because what I've done for you is while you're taking the test, I uploaded in content a spreadsheet. So if you go to D2L, and this is a different look. Where's mine? Oh, that's I see. I don't have a smartphone, so those things look weird to me. PE5613 in content. Example problem data. See if this opens for you. Okay, now, we're always going to do this differently. I'm just going to click on it, I'm going to do a Control A, a Control C, come back into this spreadsheet that I've been working on. See, I've been working over here, I just added a sheet over here, come up to A1 and do a Control V. It's just data. There's no Visual Basic, there's no calculations. And so I've set this up for you. What is this? How do I get rid of this? Can't get rid of it. Okay. So here's a problem. We're going to calculate permanent skin, just like the last one. But our data looks a little different. Log of time, let's make it a semi-log plot. So we have production rate at a constant pressure. This is called a constant pressure drawdown. I'm producing the well at constant pressure. Doing this example right here. I know. Analysis, it says a variable rate gas flow test. It's true. the rates vary. The rates varied on example 6.1. They're varying on 6.2. But on 6.1, they were allowed to go any way they wanted to, up or down. If you produce a well at constant bottom hole flowing pressure, the rates are monotonically going to go down. So a gas well was produced at constant bottom hole pressure, 1,000 pounds. Data were summarized, and not only they're summarized in table point 4, I've listed them out for you. I've already keyed in the information, because I knew we weren't going to have a lot of time tonight. And we'll at least get started on this problem.
Sorry, where did you plot?
What?
Okay.
This is from our textbook, right? You all with me? Example 6.2, you can see why I got a cut-paste operation, because I had cut the top part of the problem from that page, and then the rest of it is right here. That's why I got a cut-and-paste problem. So here's the data that I've already put in your spreadsheet. See, I've already put this data in your spreadsheet, and I put the information in this table. Time rate from 2.4 hours to 216 hours. Here's this 400, 300 rates declining. Everything on this page already in your spreadsheet. How many people are here? Get the spread. You've copied all the 6.2 data into the workbook that you're working on because it has the Visual Basic.
Just do log base 10.
Pardon?
It's log base 10
Yeah.
on the bottom.
It's obvious from the scale, right? I didn't take any logs. I just, when you hit logarithmic, you can't get, as far as I can know of, a log base E or any other log base in Excel other than log base 10.
You can change it.
But since you asked, another important distinction between Chapter 6 and Chapter 9 is in Chapter 6, which is an older science. Transient pressure analysis is an older science than decline curve analysis. Besides having different time units, all your ARPS equations use natural logs, and all your equations in Chapter 6 use log base 10. Things to remember. Okay, everybody here now? Now, I'm probably not going to solve for permanent skin based on the time. What I'm going to do tonight, and this isn't the slope I'm looking for, by the way, as you'll see in the textbook. I'm really going to have to calculate reciprocal rate. And it's going to be the way the textbook does it, although that's not the way I would normally do it, is delta P apparent or normalized over rate. We'll make the plot so that you'll know that we can do this. That's symbol. I think I got to enter it and then edit it. Delta PA, I want a capital P.
It was delta P apparent divided by Q.
Yep. Equals. My delta P, this is given in the problem, there's apparent, remember this is the pseudo pressure multiplied by a constant. That equation right there, there's my, here in the textbook they call it normalized, but here in the problem they're calling it apparent. They're giving us those numbers though. I would normally not do this because it's a constant, and I'd plot the raw data. But that constant divided by Q is reciprocal rate. And that's what we're plotting, not rate, reciprocal rate. And then that should look like the textbook plot, and that's what we're going to get our slope and intersect from. So each one of our rate points is reciprocated and multiplied by the apparent pressures at initial and flowing conditions. I haven't calculated anything yet except for that column. All the data was given. But like I say, what I want to do tonight in the next 5 or so minutes is just calculate one number. I want to calculate the gas gravity because I like to know what the gas gravity is that they use for the problem.
Would you go back,
Can you please zoom in?
Those are absolute. Okay, that's where we're going to start next week. We're going to start with that plot, okay? Now, I want to calculate the gas gravity. That's my only desire before I let you guys go home. I'm not going to calculate it, I'm going to model it. Now, how am I going to do that? Who's got a strategy? Because you're going to have to do these for all these homework problems. Who's got a strategy? And this should have been my test question. How are you going to determine your gas gravity?
Given what?
Given everything you've got on this page, given everything you've got on this page. Everything I highlighted there in that box, what you're given. What's that?
Matching properties up?
Yes, matching properties up. Which properties you want to match up?
Viscosity, VG.
Viscosity's not my favorite one, but
Both of them just getting close.
which one? Viscosity and what?
Just kind of making sure both of them are.
Yeah, viscosity and what?
VG, we're going to volume back.
B sub G, good. Okay, so I've already set you up because they always give it to me in what I call oil filled units, reservoir barrels per MCF. And so I've already done the 5.61458 and 1,000 and got it in reservoir cubic feet per standard cubic feet. And yeah, so if I was going to calculate VG average, I should put these are all givens. Okay? And then I've set myself up to calculate the same things. Okay? And it's also important to note that, where's my copy paste? from my PowerPoint. A gas well was produced at constant known as average gas properties are evaluated at the arithmetic average of initial and bottom hole flowing pressures. You add them up, divide by 2 and get 2825. Add them up. Divide by 2 and you get 2825. So that's the pressure I'm going to calculate my B sub G at. Now, we don't know gas gravity, but we have to guess one. Who wants to make a guess?
Gravity,
Huh?
0.9.
0.9. Not 0.09, but 0.9. So we would get a gas, I call it gas, and you may have a different board because we played with this for you guys a little bit. Pressure, they told me, they calculate them all at arithmetic average. I'm going to have 4 in case I won't, I like that clever technique of copying a cell and then changing the name. And they didn't tell me if there's any impurities, so I'm going to assume they're all 0. Okay, so how much difference is my VG than their VG? I usually start with theirs first. Oops, I need an equal sign. Equals. Open a parent. Theirs, in the correct units, minus mine, divided by theirs. That's defined as the relative error. Given the known, subtract what I got, and divide by the known. That's the relative error. Okay, I'll put it in percent. That's a 14% error. Okay, so we've all read the downloaded solver, right? How come it doesn't show? Tell me there's more. Data. Do I have to do this every time I come to class? You guys are going to get good at this.
It should be on there. I don't think you're over for now.
I just saw it. Solver. Go. I don't think it took it. What happened here?
Click go instead of okay.
Huh?
Click go instead of okay.
Okay.
There we
But
go.
what's happened with my dial-up box up here? Oh, I gotta go back to home.
Back to
Data. Solver. Set this to amend by changing my gas gravity. That didn't work. See, I got a 0 gas gravity. And we can kind of play with this. The minimum's 0.5. I got a 6% error. See, the next one's 0.6. And that's not bad. For some reason, that didn't really work that good. I'm going to go with these numbers, okay? I've done this in advance. Your idea was good, it just didn't work here. Solver didn't work. But it could have worked. Let's spend a couple minutes here.
So .67 for the Hammond.
I'm gonna change it to be relative to gas gravity and N2. I'm gonna take off my F4s, and then I'm gonna tap that down. And then I'm gonna add my relative error. I forgot to F4 my given. I'm spending time here because this is important.
You can use solver if you take the error and make it like 0.1% by changing the gamma G, and I get like 0.652.
Oh, you know what? I know what I did wrong. And typically, I like to do this. I like to square my error.
You didn't click on the error.
I've done that, and I still got the 0 too.
You already did square the error?
Yeah. Yes, sir. Yours working?
Instead of like solving to a min, I just solved it to a value really low. Like, say you want so much of an error.
Typical criteria is e to the minus 6. I see, it went past it.
There you go.
Okay, now we got a gas gravity of 0.64. We all learned something tonight. I actually ran into that problem, and then instead, I calculated my own apparent pressure, which is basically a pseudo pressure function, which uses viscosity and volume factor, and because I wanted to get on the same page as them. And I got a little bit different number, but we're gonna go with 6.4 because that worked, okay? That's all I wanted to do tonight. I got a gas gravity. Now, one of the things that we want to do is see what the CG is. The gas compressibility. How come I know there? And average pressure, temperature, this new gas gravity that we solved for, impurities. Don't forget to get that last one or you'll get a value. And then my gas saturation should be equal to their given CT divided by my CG. And I got a reasonable value. How come I can't get 65%? Okay? If I don't get a reasonable number there, I may have kept playing. Okay? I can live with this. Okay, so I'd try to finish up this problem between next week, and then I can go through it pretty rapidly. You're just trying to calculate perm and skin, okay? And then we'll pick up there on 6.2, right where we left off. And maybe I'll have your test graded and passed back. Okay? Oh, I copied that page. Remember, I pasted in my wrong thing. Stop. Mic off. Critical point is only one point. You can draw the envelope and the critical point anywhere you you want to do.
You don't follow this one.
Once you draw it though, then anything to the left soil and the right hand. Oh. Anything to the right of the envelope itself
Yeah.
is dry gas.
I guess I'm trying to.
The composition.
Kind of like
No. You're missing the whole point. There's just one pretty one. Just draw it, put it somewhere.
Yeah.
Just put it.
Oh, okay.
Just, I don't care, just put a critical point on it.
So you want it on this.
Just one critical point.
That's why I did 3 different.
That's fine. That's fine.
Well, I understand what you're saying.
Yeah, but just, given a fluid composition, you're only gonna have one fluid envelope and one critical point.
Yeah, so with those 3.
Yeah, then to the left, or to the right, there's your 3 cases for condensate, wet gas, and dry gas.
And then the other thing on the reservoir. Trying to. I don't like when you do the equation that shows the critical point is,
Has nothing to do with the critical point.
well, I'm trying to relate that with the trichotomy.
Well, anything between the critical point and the trichotomy is a retrograde.
Which is the same as.
Yes, retrograde condensate.
And when you
But
go there, you.
the trouble is the word condensate as used in the field, they're not looking at a phase diagram. They just see that there's liquid in the separator. That's called condensate. So you can't tell from the surface whether it's a wet gas reservoir that produced condensate at the surface because the path of production generated the liquid, or if it's a condensate reservoir. So if we do know, then we usually say retrograde condensate reservoir, because these quality lines are such that you enter one and then exit one, so it has retrograde behavior, like some of the planets in the solar system have. Saturn may be appearing this way and then it's going backwards. They call that retrograde motion. And so your saturations could increase, but then they could decrease as you continue. It's not monotonic, that once you develop liquid phase, that it increases. It's retrograde, so it increases for a while and then decreases.
And do we have to get the line all the way down?
Well,
Because I stopped
you
like
may not ever actually hit the retrograde portion during depletion. It could be that you reach your economic limit before then. All wells stop producing when the cost to produce them exceeds the value of the product. So you may not, theoretically, practically, you may not enter the retrograde portion of a retrograde. But by definition, it's a retrograde if the pressures between the critical point and the cricometer. It has to pass the quality lines twice. It has to intersect them twice.
But then the test I did stop in the phase diagram.
It doesn't matter where it stops. As long as you got a point on that line between here and here, retrograde comes.
Yeah, the whole significance of the critical point is what I guess.
Yeah. You
I've
don't
always
look-
had trouble.
The critical point and the phase envelope are defined by composition.
Thank you.